Hey guys! Today we're going to practice identifying when we need to change the order of integration in a triple integral. We're going to figure out how to find the new limits of integration when we do need to change, and how to preserve which direction we are integrating. I know that a lot of my students were struggling with this, so I think this is a good thing that we should practice before the next exam. So we're going to try to compute this triple integral. It's very similar to ones we've seen before, but just different enough to provide a new challenge. So whenever we're given a triple integral, our first thing is just try to tackle the inner integral and see what happens. So let's copy our integral. And our first integral, remember, is the inside one. So first we're going to try to compute the x integral. Z squared secant squared y to the 7th is constant in x. So I just get x squared over 2 times that whole thing. So we're left with the integral from 4 to 0, the integral from 2 to rad z of x squared over 2, z squared secant squared y to the 7th. And we're going to evaluate that from x equals 1 to x equals 4. And then we'll do the y and the z integrals. All right, so let's plug that in. If I plug in 4 squared over 2 is 8. 1 squared over 2 is 1/2. So we are left with 8 minus 1/2 is 15 over 2. And I can go ahead and just pull that right outside of all of the integrals because it's just a constant. The x squared over 2 has gone away because we have plugged that in. Secant squared y to the 7th dy dz. Okay, so just looking at this thing, we don't know the integral of secant squared y to the 7th off the top of our head. The z squared, that's just a constant, so it doesn't really help us. Whenever we have a trig function of something, we want to try u substitution where u is the thing inside. But if I go ahead and try it, u equals y, try a thicker pen, u equals y to the 7th will give me that du is 7y to the 6th dy. Oh, sorry. Will give me that du is 7y to the 6th dy. And the 7's easy to deal with, but we don't have a y to the 6th to cancel out with. So we'll end up with an integral in terms of y and u, and that isn't really something that we know how to work with. So we're not going to do that. And so we're left with no options, right? There is no way for us to compute this y integral. We have no technique to do this. So the only thing left to do is try not computing the y integral. And the only thing we can do instead is compute the z integral. So we know we have to switch the order of integration. Let's write this down. We switch the order of integration because there is nothing left to do. Switching the order of integration is a sort of last resort because it is tricky and it only makes things better if it's the only thing to do. And I'll give you a hint. The problems we design will always be doable by you guys. So if you can't do the y integral, switching the bounds will work. Switching the order will work. We need to figure out our new bound. And when we want to switch the order of integration, remember the thing we always do first, is we draw it. It being the region we're integrating over. So let's go ahead and draw the region we want to integrate over. Well, I'm integrating in the YZ plane. So let's go ahead and draw the YZ plane somewhere down. I'll label this one Z and this one Y. All right. And our bounds are, well, the inner limit most integral sign is for Y. So we are given Y goes from 2 to Y goes to rad Z. So Y equals 2 is right here. And Y equals rad Z should look like this. right? Because if y equals rad z, then we have that z is y squared. And we only drew the positive part because we have y as the positive square root. If you want to continue it, that's fine. It continues a little bit on the left. We are also given z goes from 4 to 0. And I know that z equals 4 should intersect my function y equals the square root of z, because 4 is 2 squared. That's 4, and then 0 was our axis, which we've already drawn. Okay, so we're left with a lot of different regions that we could be integrating over. We have to figure out which one. And the way we do that is we follow the integral. So it starts at y equals 2. We start on the bottom of the rightmost one. So I'm starting at this line. Let's maybe draw it a little bit higher up. So I'm starting at this whole line, and I'm going towards rad z, because that is the upper y limit. So if I start at this line and I move towards rad z, then I am highlighting this part. So we're starting at the line y equals 2, and we're moving towards the curve y equals the square root of z. So I'm going to highlight everything in between. So I'm including this part. I'm including this part. And there's nothing really on the bottom because this curve does not exist below here. There's no square root of a negative. All right. Now we need to figure out which part of this we're using, and we're told from the next integral that we're going from 4 to 0. So we are going in this piece, new orange one. Because that is the one that is between y equals 2, y equals the square root of z, and also between z equals 4 and z equals 0. Excellent. Now that we've identified the region, we have to figure out which order it goes in. Does it go left to right, top to bottom? Does it go bottom to top, left to right? Lots of different possibilities. So the first one we did was y, and second was z. And y went from 2 to rad z. So I'm going back and I'm looking at the region that we ended up highlighting in orange. Well, 2 is on the right and rad z is on the left. So we went right to left. We want to keep track of that when we're figuring out our new limits of integration. And then let's figure out z. Z started at 4 and went to 0. And 4 is on the top and 0 is on the bottom. So we went top to bottom. Okay. So now we're going to switch the order. We're going to do z first and then we're going to do y. But we don't want to change the direction. It's very important that we preserve the direction of our integral. Otherwise, we might end up with a minus sign. We'll get the negative of the integral that we should get. So now, we haven't figured out what our bounds are yet. But we know we're going from z to y, from z first, then y. And we know that y goes right to left and that z goes top to bottom. So we're just switching the order of y and z. We're not switching any of the orders left to right, top to bottom, the ones that are across the arrows. Okay, so now we should figure out what's on top in the z direction and what's on bottom in the z direction. So let's go back to our region. The thing on top of it is this curve. And this is the curve y equals the square root of z. But since we're solving for z, now we're considering it to be the curve z equals y squared. So the thing I will fill in right here is y squared. Then on the bottom is this curve. This is just the line z equals 0. So we went from y squared to 0 now. So these are the limits of our z integral. And next we need to figure out the limits of our y integral. Well, on the right is just the line y equals 2. Oops. So we go from 2. And then what is on the left? Well, it's kind of hard to see. It should be this line. And we know it's just a line because we want it to be a constant, right? If we had a variable at the end, it wouldn't make sense. we know that the outermost integral should only have constants as our limit. That's a rule for our class. So it should be the line y equals 0. So let's rewrite this integral with our new limits of integration. So we're left with the 15 halves stayed the same. And now we've got dz and then dy. Our integrand doesn't change at all. And our new z limits, we said, went from top to bottom, was y squared to 0. And remember, y squared then gets written on the bottom. I know it's a little weird, top and bottom. And then we've got our y limits. We said we started at 2 and we went to 0. We're integrating from 2 to 0. Okay, so now let's try actually computing this integral. We said we couldn't do the y integral, so let's try the z integral. And secant squared y to the 7th is just constant in z. So we're just integrating z squared, which we know should be z cubed over 3. Secant squared y to the 7th stays the same. It's just a constant. I will evaluate from z goes from y squared to 0. And then we will do our y integral. Everything else will stay the same. All right. Well, if I plug in 0, it just goes away. So the only term that will stick around is the one where z is y squared. And remember, this will be subtracted. So we're going to have a minus sign comes out. Integral from 2 to 0 of y squared cubed is y to the 6th. And I can also pull out that 1/3. And then we are left with still our secant squared y to the 7th dy. And now the only thing left to do is to try u substitution. And we need to try the same substitution we tried before. U will still need to be y to the 7th. So du will still be 7y to the 6th dy. But now we do have a y to the 6th to cancel with. So I'll end up with minus 15 over 2 will stay. Let's combine that with the 1/3 to get minus 15 over 6. Or rather, minus 5 over 2. Keep things simplified. The integral from, now this isn't u equals 2 to 0, it's y equals 2 to 0. You can change your limits if you like. I prefer to leave them in terms of y and substitute back at the end. Doesn't matter. Both are acceptable. Move this over a little bit. And now we've got y to the 6th. We'll cancel with the 1 from du, and we're left with just a 1 over 7. Secant squared will stay the same, except now inside of it is just a u. And dy became du. Now let's try to do the integral. 1 over 7 just comes out. So we get minus 5 over 14. And the integral of secant squared is one that we should know from Calc 1, maybe Calc 2, if we took that more recently, is just tangent. So we're just left with the tangent of u from y equals 2 to 0. We want to keep track of which variable we're talking about, because right now we've got u's and y's floating around. So if I want to plug in y, I need to substitute that back in. I need to move our work from earlier over. I'm going to end up with just minus 5 over 14. Tangent of, remember, u was y to the 7th. And now I'm going to plug in y equals from 2 to 0. The tangent of 0 is 0, so I'm only concerned with the y equals 2 term. And that one gets subtracted, so our minus sign goes away because minus times minus. So we're left with 5 over 14 tangent of 2 to the 7th power, which we don't need to simplify. And so this should be our final answer. So in this problem, we practiced computing triple integrals in Cartesian coordinates, identifying the need to switch the orders of integration, and actually doing the switching and figuring out our new limits while preserving the direction of integration. That's all.